in the book. Okay. Okay, so let's just stop, slow down. I'm pretty proud of my little picture here. Now, obviously, this represents a car driving, and you're all familiar with Doppler, whether you know it or not. You go out on I-10 and you listen to cars whizzing by, especially if one of them has their horn on because you're standing out there, and the pitch is high, and it passes. You goes, oh, it's low. The pitch change is a frequency change. Well, why is that frequency? The sound of that horn is a steady. There's a steady frequency coming out of that horn, although it's effectively being changed. So if we were to, let me just quickly draw this car, or at least this horn. I'll do my little. Little bulb at the end there. There's my horn. And if it's staying still and we're going to create a sound wave coming from it, well, it's going to look something like whoops, a little bit off there. Okay. So a stationary horn, stationary red blood cell, a stationary whatever, that's either creating noise or reflecting noise in the case of red blood cells, doesn't have a Doppler shift. The frequency is the same. The wavelength all right, let's just do a straight line. Wavelength there is equal, I know I didn't draw this perfectly, is equal to the wavelength there. There we go. You take that horn and you move it, and in the direction that the horn is going, it's like it makes the sound wave, but then it's catching up to its own sound wave. So effectively, it's shortening the wavelength in the direction of sound, or in the direction of travel of the sound creator, in this case a horn. And on the other side, where the car is running away from its own sound, the wavelength is much longer. Now, if I could draw this in real time, you would see that each one of these waves actually originated. They all originate from a car that's moving. So let's see, this circle here, when the front of the car, which is now here, at least that horn is right there, that horn was at one time back here. And so it created, you really are a piece of work, Kurt. You created a sound wave, a sound bubble, and went out like that. I was a little bit off on that, but you get the idea. So that's all a Doppler is. It's compressing a wave or stretching it out. In the case of ultrasound, the red blood cells aren't creating their own sound. they're reflecting sound. And so we put a frequency in. That frequency, let's see, let's make a little purple. That's coming in. And that has a certain wavelength associated with it. But then as it comes around here, it bounces back off. This wave now becomes this echo. The spatial pulse length has changed because, well, I don't want to say spatial pulse length, because it's no longer a pulse when it's an echo. It's just a mess of echoes. But the lambda changes. Lambda, let's just say it was that long to begin with. It bounces off of there, becomes compressed, and now lambda, or wavelength, has been compressed. Effectively a different frequency. Now with the car, that happens once. With the policeman over here, police car. With the police car, he has to send out a pulse of sound. It runs into the car. Let's see, how would you say this? The car runs into that sound. The car is not stationary while the sound is coming out. The sound is going towards the car. That effectively shortens the wavelength. I know it's a little hard to picture why. I've got another example I've told you guys before, but then on the reflection itself, the echo itself is now being compressed again. So with the police car, it's 2 times is the sound compressed, or the wavelength is shortened twice. If the sound is over here, this is only 1 time that the sound has been shortened. The other example I give is as far as the, let's say from the policeman's point of view, or from the sonographer's transducer point of view, is that we're sending out our signal kind of like running. The difference between standing at the ocean and letting the waves hit you versus running out into the ocean, and the waves are going to hit you faster because you're going to meet them faster. So that's kind of the number one. That's the first shift. And then if you create an echo from that, that would be the second shift. But obviously, creating an echo in the ocean with your feet running into it, the analogy breaks down. Let's just put it that way. So we have an easy equation, and then we have a harder equation. The easy equation is simply Doppler shift is equal to the reflected frequency minus the transmitted frequency. That can give us a positive shift or a negative shift. Doesn't have to be always positive. So that car, in essence, could be driving away from you. Cops can catch you when you're driving away from them just as easily as they can catch you when you're driving towards them. Their Doppler works identically, really, both ways. So reflected frequency minus transmitted frequency. The happy accident, and we're going to write that down. I like ultrasound has a lot of happy accidents. The happy accident of Doppler ultrasound is that, let's say we put in 5 million hertz. That's your transmitted frequency. I also like to say F0. Your functional, your operational frequency is 5,000 hertz. But the reflected frequency, the frequency that comes back to the transducer, is now, did I say 5,000? I meant 5 million. 5 million and 0, 20, let's see, it's 20. Oh. Goes from 20 to 20,000. So let's just make this 500, right? That's one possibility. Or let's just write another possibility in. Whoops, that's not FO. FR, reflected. Or we could have F reflected is equal to 4,999 or 98,500 hertz. So it could be a positive Doppler shift. That blood was coming towards you. The frequency, if the frequency is higher, it's a positive. If the frequency is smaller, it's now a negative, because that blood cell is going away from you. But in either case, we have a Doppler shift of 500 hertz. And the happy accident, as we said, what? Human hearing is 20 to 20,000 hertz. That's a large amount. That's a lot of hertz. But yeah, the happy accident is that when blood shifts, when frequency shifts, it is within our hearing range. And so there's nothing else for the machine to do other than to really subtract out the original frequency and just display, or also auditory and put over our speakers, the actual frequency created, which just happens to be within human hearing. So that's all they have to do. All right. Just a little difference between speed. That's just like speed. Your actual speed, your gross speed, what you are actually traveling. Velocity is kind of like a vector. If you know what a vector means, is speed plus direction. Yeah, direction. We talk about velocity because, well, why? I mean, we could just, if we said the word speed, I think, the speed of the blood is 100 centimeters per second. Everyone knows what you're talking about when we talk about velocity, because really, when we find this, we need to know what the direction is. And that's when we get to our Harder equation. That's when we get to our angle correct and all that other stuff. And when we have to get that little tiny region of interest when using a spectral Doppler, everything has to be right in order to get the correct velocity, speed, but velocity. they're not that different when it comes to terminology, I guess. So then we run into our Doppler shift equation. And we've talked about this before. Two, that comes from two Doppler shifts. The red blood cell is coming towards the sound. That, in effect, causes a shift. The sound hits the red blood cell. It creates an echo. That echo is kind of like the red blood cell is now the creator of sound. I mean, obviously, it's just reflecting sound, but now it's the creator of sound, and it's following its own path. And so that's the second shift in Doppler. Velocity of blood, well, that's really what we're looking for, right? Transducer frequency, okay. So frequency matters when we talk about Doppler. It's kind of the last thing. Very few sonographers, including yours truly, ever really mess with the frequency when we're trying to get a better Doppler signal, but it is something we can do. And the cosine of theta, multiplied by the cosine of theta. This is where things get a little important as far as steering and as far as angle correcting. But really, I would say the steering is more important. Or heel, toe. Steering, heel, toe. Do them in concert together. And then there's propagation speed, speed of sound. So written in a little bit cleaner way, FD for Doppler shift, 2 times V for velocity, times FO for the operating frequency of the transducer, times the cosine theta. We're going to talk a little bit more about cosine theta, divided by C, 1.54. All right. So let's look at this. This chart can be found on page 310. And these are your angles. These are several possible angles of attack on a vessel. So if you have a 0 degrees, what that actually means is that let's just quickly draw a 0 degree angle. Let's see, here's our transducer is no. Our transducer is off, looking in that direction, and our blood vessel is basically straight at it, and little red blood cells are in there. And everything is coming directly at the transducer or directly away, does not matter. That's an angle 0. You could see the cosine of angle 0 is 1. The cosine of 180 degrees, which would be basically just blood going the other way. It's going away from you. So it's 180 degrees. It's equivalent to 0, really. So that is -1, but they're both 1, which means right here, this equation, the largest number that can ever fit in that equation is 1. And if you're going to fit 1 in there, then it doesn't even matter. It's as if that doesn't even exist. Well, that's because at a cosine 0, or I'm sorry, an angle 0 or an angle 180 degrees, you don't need that part of the equation anymore. It is what it is. The velocity, the speed and the velocity are basically identical. They are the same thing. It is what it is. 30-degree angle or 150-degree angle, our cosine is 0.87. So then, you know, what I would say, instead of having cosine theta, we would actually, the number would be 0.87 at a 30-degree angle. So that's not considered too bad. It's pretty close to 1, but it is inaccurate. 1 is 100% accurate. Anything less than 1 starts to become inaccurate. At 60 degrees, we're now at, instead of 0.87, we're at 0.5. Let's put that in brackets there. Now, our accuracy is literally half. What does that mean? If I put a 0.5 in the numerator rather than a 1, I've basically when we well, for Doppler shift, that's fine. Let's do Doppler shift. The Doppler shift would be 1/2 of what it really should be. So now that's even more inaccurate. I wish they had something like 70 degrees or 80 degrees, but let's just guesstimate. I could use a calculator real quickly, but at an angle 70 degrees, 70 degrees, let's just say it's, I'll use a different color, 0. I don't know, 4, whatever. Whatever, I don't know what it really is, so just, you know, obviously use numbers. 0.4.
0.34.
Thank you. 0.34, that's a 3/4 there. Way too inaccurate. So, here's why we have, I've already told you guys why during a carotid exam we keep things at 60. Well, there's 2 reasons. One is because there's been 1,000 studies done, all of them at standard 60 degrees. If you start using 30 degrees, it's inaccurate, but not as inaccurate. If you go to 70 degrees, it's really inaccurate. So what they've done is they just said, you know what, 60 degrees, 50% inaccurate, we could handle that. And all the studies were at 60 degrees. So let's just make that the standard. And the other reason why it's the standard, of course, is because it's very hard to get 0 degrees. It's even hard to get 30 degrees on most carotids. So 60 degrees is at that point of where you have an acceptable inaccuracy. Beyond that, the inaccuracy kind of, it's like logarithmic. It goes higher and higher and higher, up to the point where when you get to 90 degrees, the cosine is 0. If you put a 0 here, then when you have a 0 in your equation in the numerator, 2 times velocity times the frequency times 0 divided by speed of sound, guess what? You get 0 Doppler shift. All the other numbers don't matter. Once you have a 0 in there, the answer is 0. Now, there are reasons why even in color Doppler at a 0-degree angle, you sometimes get a little bit of color, and that's literally because you're getting a tiny degree on one side and a tiny degree on the other side. So, well, actually, I shouldn't say a tiny degree. I should very high degree, but a little bit less than 90 on one side, a little bit more than 90 on the other side. So you're just off of 0. That's why you get some Doppler shift, but it's very inaccurate. So some of you have noticed, by the way, that your waveform is kind of weak. And then I come by and I help you and I say, well, you know what, let's really dig your heel in on this one, or let's steer just a little bit more. Suddenly that very same waveform, the very same location in the blood vessel, without changing anything else other than your angle of attack, suddenly it goes like that, which is better, by the way. It's always better. But this will be a little hint on something else. Well, that's because we've decreased. We've gone from, let's say, maybe a 60 degrees, and we've dropped it down to 30 degrees, a little more accurate. Or we went from 30 degrees and all the way down to a 0 degrees. Now it's super accurate. In fact, it's 100% accurate. So that's interesting. Let me do something here. Let's see, how would I? So we know what aliasing is. We're going to talk more about it today, but you generally know what aliasing is. Aliasing is when you've gone beyond your current scale and the computer doesn't have a scale for you, so it wraps around. Now, normally we could handle that by simply changing our PRF, pulse repetition frequency, and that changes our scale. We could move our baseline. That doesn't really change our scale, but it might help anyway. But there are some times that you just can't fix it. Well, so one thing to do is I got to think about the cosine here. Let me erase one more thing. Since the cosine of the angle is kind of like the opposite of like 0 is 1 and 60 is 0.5 and 90 is 0, blah, blah, blah. You know, it's kind of opposites. I want to draw my arrows, you know, my up-down arrows for equations. Draw my arrows a little bit over here. Okay. Let's use bright colors. I guess it's pretty bright. Okay. Let's just start with velocity. We increase our velocity. Everything on top, if you increase it, you increase the numerator, you increase the product, in this case, Doppler shift. So velocity, of course, our shift is going to be greater with more velocity. That makes sense. Frequency. This is the one where very few sonographers actually do this, but if we increase our frequency, that also increases our Doppler shift. That's kind of interesting. Let's use red. Now, if we decrease our angle, in other words, increase our cosine. So if we have a cosine of 1, that's as big of an arrow. I'm putting the arrow over here because I don't want to confuse the angle, which needs to be small in order to make a big shift. So I'm going to put my arrow over here. Is going to make a good size Doppler shift. And let's, you know what, let's do a different color here. We'll do a burnt orange for University of Texas. We're also in, right? You know, UT at, I can't think. Anyway, 60 degrees. That too is an up arrow, but not as much. Let's make it smaller. Let's make this arrow tiny. Little tiny arrow here equates to a smaller Doppler shift. It's still a Doppler shift, so we're still getting something. And we can just as easily say the same thing over here for the negatives. The negative Doppler shifts are shifting exactly as the positive Doppler shifts are shifting. Shifty shift. So what does that mean for aliasing? Let's say we're aliasing so badly, in other words, the velocity is so high that we can't fix it with PRF alone. We've turned our PRF all the way up. We're still aliasing, and specifically, we're aliasing on the spectral. Okay, well, we can't really change our velocity. So velocity is velocity. That's going to stay the same. We can look at our frequency and say, you know what? Let's go down in frequency. That's going to produce a downward Doppler shift. That's something I don't do, but I can. You know, if I have aliasing, I could take my Doppler. My frequency in Doppler, and just try clicking it down. That will make a change in the Doppler shift. The Doppler shift will not be as great because we went down. And the numerator, we have a down arrow in the numerator. And cosine. And so we've already said that, let's bring this over here. Instead of using 0 degree angle and having aliasing, and we've tried everything else and we still have aliasing, get a little bit worse of an angle. I hope that's not confusing the way I'm putting these arrows in. Here, I'll go ahead and put the arrow over here. If I have a worse angle, I have less Doppler shift. So even though 9 times out of 10, I'm going to tell you 99 times out of 100, I'm going to tell you to get the best Doppler angle you can get. Sometimes, in order to fit everything on the screen, we actually ruin our angle. Now that's a good SPI question, by the way, guys. And to understand how this equation works, just remember that cosine is opposite of the angle. So a good angle is 0. It gives us a larger cosine. I am not going to go over this, but I just want to just mention that, and I'm not going to go over this because I'm not very good at it at all, but just, what is this, algebra? Sine, cosine, tangent. The sine is opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. You don't even have to know this at all. You don't have to understand this at all. I just want to remind you that this, when we say sine, that's what really we're talking about, a triangle, basically, and measuring a triangle. Let me just run over here. I forgot about my little picture here. Do I want to be here? Nah, let me get back to that. I'm definitely going to have to go through my book and make sure I didn't skip anything here, because I'm kind of going off the cuff. All right, so let me draw in an actual vector. A vector meaning the direction and velocity of flow. Okay. So that's our standard vector. That's the way the red blood cells are flowing. They're going from right to left on the screen. I captured, at this moment in time, there is a red blood cell inside of my region of interest. I want to know what my cosine is. There's my theta angle. I could measure it from over here. Same difference. So that is the one we want to keep 60 degrees. And that looks to be about 60 degrees or less. Now, let's mention there's something I have a region of interest here, but it's missing something, isn't it? There we go. My angle correct. The angle correct tells the computer the computer has that equation built into it. It actually solves for velocity for us, but it has the Doppler shift equation into it. The angle correct is telling us the difference between, is basically telling us, well, this. If you don't have an angle correct at all, the computer has to assume a 0 and we'll put 1 in the equation. 1 being the largest number. And so you're gonna, oh, is that gonna be overestimate? Yeah, you'll what, now I can't think. It would seem like it would underestimate. Well, in any case. you now have an incorrect velocity. If your angle correct is off, if your angle correct is off, then, and let's just do this with a different color. Let's say that's your angle correct. Well, you're not correcting for anything. You're not telling the computer what the actual vector is. That's really what an angle correct is. A vector is speed and direction. Speed and direction of the red blood cells. Angle correct tells the computer what that actual vector is. It tells the computer what theta is. If I'm steered in this direction, but have well, basically, I just made 90 degrees, didn't I? I didn't mean it. But if I'm steered in that direction, I'm telling the computer that this is what theta is. And just by total accident, I basically made this 90 degrees. And technically speaking, I probably shouldn't get any blood flow at all, because any Doppler shift at all. Practically speaking, I usually get something, but that would be an incorrect use of the angle correct. And as we steer more or less, that changes our angle correct as well. And so you could steer a lot more. And of course, we know that steering with our machines is not always the best because of sensitivity. But if you steer more, you get smaller and smaller thetas, which is good. We want a small theta because that's more accurate. It's not always practical. Okay. So I've drawn just a couple, I've got a couple things of aliasing in here. So we know this aliasing is so bad that peak systole has gone past the top, through the bottom, and it's even crossed the baseline. It's possible to have aliasing so bad that it goes around twice. And so peak systole wraps around and then wraps around again. It's certainly possible to do that. And so lowering the baseline on this one, not going to be enough, is it? So we change our PRF. We take our little PRF button, and we're going to decrease it. Pulse repetition frequency. What does it even mean to change the pulse rep? Like why? It's a sampling rate. We're always sampling. We always have a sampling rate with pulsed ultrasound, whether it's grayscale or pulse wave like this. There's always a sampling rate. And did I say, you guys didn't stop me.
I tried.
Yeah, PRF up. Sorry, guys. I'm glad I remembered, because, you know, God knows John wasn't going to do anything about it.
If you look at your messages, you'll know.
Okay. Yeah, PRF sampling. So why? We need to sample enough times for the machine to understand what it's looking at. It's kind of like sampling is like playing around with a strobe light. And if the strobe is really fast, well, we actually see that all the time. When you're in a room lit by ballasted fluorescent lights, you're actually in a strobe light environment. If we could see what was actually going on, those fluorescent lights are on and off and on and off. That's why they cause headaches in some people, by the way. So those are strobing so fast that we have no aliasing. We know exactly what's going on, but then we play with an actual strobe light. You turn the lights off, and we start dancing around, and John's over in the corner doing some kind of weird ass dance, but all you see is occasionally he's, he looks kind of cool, but then you turn the sampling rate up and you realize, no, he looks like a total idiot. And that's a sampling rate. So if our sampling rate's not high enough, we get incorrect information. So we have to turn our PRF up. The problem with PRF being too high is that we're not able to sample the really slow velocities. So we turn our PRF down low when we're looking at slow blood flow. We turn up high for high blood flow. So let's say we turned our PRF all the way up. We took our baseline down. We still have aliasing. What else can we do? Let's look at that. 2 times the velocity of blood. Can't change 2, you can't change the velocity of blood. Oh, we could change our frequency. So I could say, I could turn my frequency down, and that will actually decrease the Doppler shift.
Couldn't you just move the transducer to a better location so it's not as far?
Yeah, you're a little quiet there, but I think I heard you. Yeah, absolutely. You could. So depth, changing your velocity, or I'm sorry, changing your transducer is one thing, because now you're dealing with a totally different frequency range. Changing your location, one thing I'll tell my students is push, even on a carotid. If you're on the carotid, now I don't want you to push and drag the transducer all over the place. You'll either choke them out or make them pass out. But if you're on one particular spot, especially if it's off the trachea and you're just not quite getting it, go ahead and give a little bit of a push. One of the things that pushing does, it gets your transducer half a centimeter closer, and sometimes that's all it takes to make a difference. It also compresses the tissue, that's a different story. But getting it a little closer. Why does that matter? Because depth changes your PRF automatically. We have, in Doppler, we have control over our PRF, but there's still things that are automatic. And so if you're Dopplering at 1 centimeter versus 10 centimeters, it's automatically going to set you up with a PRF that can handle 10 centimeters versus 1 centimeter. So if you get closer, if you get your transducer somehow closer to that vessel, you can increase your PRF even more. So even beyond, let's say you maxed out here, you're maxed out at 5 centimeters, but you're not maxed out at 4 centimeters. So you change your transducer position, you push a little harder, you get to 4 centimeters. Now you get just a little bit more PRF, and maybe now you could actually fit everything onto the onto the screen. So what's the last thing? Cosine. Maybe we're getting this at, maybe we're at 50 degrees. Angle, 50-degree angle. Well, either toe heel less or steer less, make that theta 60 degrees, and suddenly these peaks will get smaller. Just don't go to 65 degrees because the doctor will yell at you. All right. Color Doppler, of course, has aliasing too. That's really important. When we have, let's see. Well, I have two here. We'll cover that really quickly. Let's say I have, and we'll do the same over here. 30 and 30. So, and I still have never been able to understand why 30 centimeters when, like our carotids, they start out at 30 centimeters per second and we really don't get anything. So I tell you guys, knock it down to about 20 centimeters per second. And then, and then we get some color in there, but the actual velocity of the blood is like 100 centimeters per second. So I'm not 100% sure why, but we do get a little bit of aliasing when that happens. So of course, as you guys know, aliasing is just a wrap around. You've gone beyond the scale. It wraps around. So it goes from a red-yellow to a light blue color. There's no black in between. It goes from red to blue, that's a reversal of flow, and that's different. Just be aware of that. Before we go on any farther, just because the picture is right here, we don't really use this in general ultrasound, but what is this called again? It's turbulence. It's variation. It's even before I got to the page, I remembered it. Variance. Variance. And turn my volume back down. Variance mode. So echo techs use this. It basically shows, like if you already have blue with greens in it or red with yellows with it, I kind of use yellow and yellow on this one, that's all right. That shows turbulence. It's how much it's varying from one direction. Okay. What was I going to even show with this? I don't remember. Okay, so I have a color Doppler box. Yeah, there's a bunch of things. I'm going to have to go over the book. I'm sure I'm glossing over some things, so I'll go over the book. 11 o'clock, which should be good. Color uses I don't want to say equation, but a calculation called autocorrelation. autocorrelation is the it's not calculation, it was calculation. It's fun, it's good enough. When the color is on, the entire box is your region of interest. Your ROI is up here. Your ROI is down here. Your ROI is right here where it should be. All of those are different areas. The entire box is one big region of interest. Autocorrelation is a program, a calculation that takes a large amount of information and can gather some useful information out of that. A large amount of data and gather some useful information out of it. Because of that, because the region of interest is so large, color Doppler using autocorrelation cannot really give us velocities. We can guesstimate velocity, but that's not even accurate. You can't even really guesstimate a velocity because, gosh, you look at what the actual velocity scale is on a color map, it doesn't really correlate. I still don't know why. Now, if we are over here with our color box and we're getting aliasing, that means our PRF is too low. We need to increase our PRF, or you hit pause and you trackball back a couple of frames until you get one solid color. Either one's fine. You don't want aliasing where it doesn't belong. Aliasing does not belong in that smaller color box because there's nothing going on. Aliasing does belong in this larger box because velocity has increased, and that's what we want to see. In fact, if your PRF is too high, yes, if it's too high, you could actually miss aliasing in color Doppler. So aliasing here is very helpful. Go back and look at here, it is aliasing never, whoops, helpful. So we never really want to see aliasing in spectral Doppler. In color Doppler, we do want to see it if it's telling us important information. Your image on page 325, that's actually blood flow in and out of a kidney. Their scale is 0.14 centimeters per second, which is too small. And so we have aliasing all over that kidney in color, and that's not helpful. Having said that, in the case of a kidney where getting blood flow throughout the kidney is difficult, you might put up with aliasing just to show blood flow. But in general, we don't want to see that. We would rather see red in and blue out. Oh man, so. Okay, Doppler equation, I'm fine. No. Doppler shifting to the frequency, yes, Doppler shifting. Oh, bidirectional Doppler, I really didn't talk about that, but I kind of did. The most, oh, and another term which I fail to use a lot, and so I got to make sure that I use this term more often. Actually, let me. Oh, I got, I still have continuous wave to talk about. All right, let's talk about this bidirectional. I'm sorry, I know I'm a little bit all over today. Page 311. Hi. Whose class are you in anyway? If I have grayscale up here, Doppler here, two things at once, it is a duplex exam. Sorry, my little cheater didn't help me there. Grayscale. So you're doing duplex all the time when you're doing a it's a duplex exam of the carotid arteries. You might see actual script for, and that just simply means that it's a grayscale and Doppler at the same time. Bidirectional Doppler, we've kind of already talked about that. If our waveform let's go ahead and just put that down here, sorry. If my waveform goes up and then back and then up and then back, there's bidirectional flow of positive, negative, positive, negative. So those are Doppler shifts, are positive and negative, positive and negative. And this can also go auditory, which is why, guys, I honestly cannot overemphasize listening to the Doppler is so important. Once you get used to what a vessel should sound like, and you're looking around and you're typing something and your hand moves slightly, and that transducer, that tiny region of interest goes over a stenosis that you didn't even know was there, or you kept on missing it. Maybe you knew it was there, but you couldn't quite find it. Suddenly you hear it, and it's like, whoa, okay, now I got it, because it goes from more of a laminar sound to a stenosis. Actually sounds like psh, psh, like you just got a hole in your tire. Psh. You get that kind of sound. It's really important to hear that. The picture on page 311 happens to be a heart with a valve problem. So they're getting reflux. And so what that echotech is seeing, but they're also hearing, is forward reversal, forward reversal. So higher frequency, lower frequency, positive shift, negative shift. So you hear the positive and negative shift just as easily as you could see it on the screen. So listening is really important, especially during my class. Continuous wave. Okay. Well, I did have plans on talking about continuous wave, so that is good. But I didn't give myself a ton of room, did I? I need this room down here. Okay. So the final and best way to get a waveform and never, ever, ever have aliasing Even if the blood's traveling 1,000 miles an hour, you will not get aliasing with a continuous wave transducer, which is pretty cool. Because why did we get aliasing before? The sampling rate wasn't high enough. When John was dancing like a maniac, but we were only sampling at a very slow rate with that light that flashes thing, strobe light. That strobe light is going slow. We only catch a little bit. We don't really know what's going on until we speed it up and speed it up and speed it up and speed it up. And then we're able to put it all together. It might still be flashy, but we're able to put it all together and say, okay, now I get what's going on in this room. Someone call a paddy wagon. So the continuous wave doesn't flash at all. It is continuous. It is a constant stream of information, or a constant beam going out, so therefore a constant unending stream of information coming back. It has two elements, a receiving element and a output element. So let's start with the output element. All right, damn it. Okay, that's more like it. Let's see, that's straight out. We're gonna turn it slightly this way. So the yellow, burnt yellow is my beam of sound. Oh. Sorry, I just leaned on one of my wires and everything went wackadoo on me. Beam of sound going out. And on the way back, are all my echoes. So advantages of this setup are high quality. Low bandwidth, that's not so much of an advantage, but the narrow bandwidth high quality actually is very sensitive. And these are good things. Sensitive. There's no backing material behind these elements, so they produce sound very easily, but even more importantly, they hear sound much better than our regular transducers. So they're very sensitive. Let's see, high quality, sensitive, oh, and never alias. Never alias. I think that's the advantages. Well, never alias, therefore, very high velocities can be recorded. The bad things, let's see, we'll use red is bad, is in sad faces. Well, the number one thing is, well, let's see, a couple. Well, there's no picture. No picture, no image is created. Just like all the way back in the beginning of the semester, we talked about thunderclouds and range, and being able to say that one flash of lightning corresponds to that sound of thunder, and if I time it, okay, I know how far away the lightning was, or the thundercloud is. Whereas if it's a constant lightning, I don't know which sound goes to which flash. That's what happens with continuous wave. There's constant sound, We don't know. We can't make a picture. And the reason we can't make a picture is because of what's called range ambiguity. Let's get a little closer so I could actually see what I'm writing here. Range ambiguity, that's no good. We don't know exactly where we are when we're scanning. We have an idea. There is an area of sensitivity, but it's only an area. It's kind of ambiguous. And there's no TGC, time gain compensation. How could you have time gain compensation? Remember, that's timing the pulse goes in and we compensate more and more and more and more. In other words, we gain more and more and more and more as those echoes are coming back. Every microsecond that goes by, we know that those echoes are going to be weaker, not necessarily because the structure is less echogenic, but because of just simply attenuation. So, but if we can't know a picture, we have range ambiguity, how are we going to do TGC? We can't. So that means things that are close are going to have vessels that are close are going to have a very strong signal. Vessels that are far away are going to have a weaker signal, simply from attenuation. And we can't fix that. The other thing about that is, if you think about it, is we could have more than one vessel. So the burnt orange yellow beam going out is angled slightly so that it hopefully crosses echoes coming back. It produces what's called the range or area of sensitivity. Probably area of sensitivity, which is going to be all in there. Which means we have an artery there. Ooh, even better. Say we have another artery over here. Whoops, those aren't red blood cells. Perhaps these two arteries are traveling at the same velocity, but the Doppler angle isn't the same. And so there's going to be confusion as to what the true velocity is. This is going to create those two vessels together are going to create one waveform. And so that's a potential issue right there. Another potential issue is although this one would be a little bit easier to understand. You have two blood vessels going in opposite directions. Of course, that happens all the time, even with pulse Doppler. You just get an artery over the baseline and a vein below the baseline. So that's a possibility. But in any case, no picture, only a waveform. So in the case that I just drew right there, we would have, let's do this in color. We might have an artery and a vein. Whoops. So venous flow below the baseline, arterial flow above. Dedicated continuous wave transducers do not use backing material. Results in the following: undampened transmitted signal, which creates a narrow bandwidth, a high quality, high sensitivity. Matching layers, of course, are going to be used. And I kind of already talked about pulse wave. Okay. Gosh, 11:20. We've already talked about most of this already. Now I tell you what, let me end it here and resume recording, because I was just flicking through here. Under aliasing, let me tell you one last thing. Then I will end today's lecture, and I will follow up with either a video or maybe some written material if I fail to talk about anything. Actually, I usually draw a couple of things out when we talk about aliasing. And so specifically, it's going to be a Nyquist limit, which is page 316. If I have points, if I have data points that are, let's say there's one there, one there, one there. Now let's just leave it with 3 data points for now. What the computer might say is, okay, I see a pattern here. And make a wave, I just missed that one, but make a wave like that. But what if that wasn't really the full story? What if there should have been a lot more data points? So, shoot, I kind of lost my, all right. You'll get the point of this anyway. So the first time we sampled, our sampling rate was kind of low. Our PRF was low. And the computer said, oh, this must be your waveform. And we looked at it and said, no, we're not comfortable with that. So we added some more points to this. And we found that, okay. This is why I usually plan this one out well in advance, because it's actually a lot harder than it looks. you get the general idea. The first time I sampled it not enough. And I found the blue line, but it was incorrect. We had incorrect information from that. By sampling more, I get the pink line and say, oh, okay, whatever weird form of waveform that is, that's what it's supposed to be. So that's sampling at a higher rate. Okay, that was pathetic. That was pathetic. So what this is actually called is the Nyquist limit. So Nyquist limit limit is equal pulse repetition frequency, that's in hertz. This is in hertz too. Divided by 2. Divided by 2. In other words, every cycle needs to have 2 sampling points. Minimum. Sampling point there. Sampling point there. Inside of every cycle. If you have less than 2 per cycle, then the computer is going to assume the wrong, well, in our case, velocity, but it's going to assume the wrong frequency, basically. So we're using pulse repetition frequency by increasing the pulse repetition frequency. We are making sure that we have correct frequency shifts. Does that make sense? Let's see. So if I go way up on my PRF, now I'm sampling many times inside of one cycle. Now we're nowhere near the Nyquist limit. In fact, this is the time where I come up and say, your color's not showing up. Turn down your pulse repetition frequency, or your waveform is too small on the screen. Turn down your pulse repetition frequency. But in any case, by having it up high, if it's high, we avoid aliasing. If it's low, we risk aliasing. Once again, with depth, when the sample volume is deep, the PRF is automatically low. And the Nyquist limit is low. So yes, in Doppler, we have control over PRF, but there's also a depth component to that. So there's beyond our control, there's also the baseline PRF with depth. So if your depth is quite deep, your PRF will be lower. If it's lower, we're risking aliasing. If we get our transducer closer to the vessel, we can raise our PRF. We can avoid aliasing. Anyway, Nyquist limit, pulse repetition frequency divided by 2. Okay. All right, mostly good today. Well, I got a little out of word, but that's okay. Let me pause or no, pause.